The Carnot cycle is a reversible cycle consisting of isothermal and adiabatic processes. In this example, I have that graphed here in this PV diagram, and I'm going to demonstrate how this graph can be imagined over here as an actual heat engine. It's not really something that could be created in reality, and in that sense, it can exist in our imagination. But as we go through it, we can definitely identify aspects of how these processes would be realized that would not really be realistic to actually build. Part of this setup is I have these two C and H labeled pieces, and they represent the hot temperature and the cold temperature. And what I can do with them is I can place them in contact with the cylinder here, and maintaining thermal equilibrium, I can allow heat to exchange between them and the cylinder as we go through this cycle. So we're starting at number 1 on the cycle, and we're going to look at that first isothermal. So that isothermal corresponds to when the engine is in contact with the hot temperature region. So that means I place this over here. And now to get from 1 to 2, we're going to imagine that heat is flowing from the hot temperature into the engine while maintaining thermal equilibrium the whole time. And it's worth appreciating that is not something you could do in reality. That is not how things really work. So we've already jumped outside the bounds of reality just in going from 1 to 2, but it is imaginable in a very theoretical kind of way. At the point 2, we're going to take away the hot temperature and then allow the system to expand adiabatically a little bit further. Now, what happens in an adiabatic expansion is just like when a soda can is opened, the gas cools down, and we saw in earlier examples that in that case that means a little mist of ice forms. But in this case, that's going to be the thing that cools this system down to a lower temperature. And we're going to let that happen until we get to part 3 in our PV diagram. And in reality, all of this is being done while equilibrium conditions are maintained inside the engine. That, again, in reality is not really possible. Once we get to that cold temperature, though, we can now, while maintaining equilibrium conditions, put the cold temperature in contact with the engine. And at this point, we're going to let it compress to bring the engine back to a state of compression so the cycle could hypothetically start over again. That means there's going to have to be heat transferred out of this engine and into the cold region as it compresses to prevent it from heating up. And again, all this would be done in thermal equilibrium, not possible in reality. Really, this thing is a mathematical contrivance that makes sense in math space, but what you have to say and do to get it to make sense physically leads to impossibilities. But nevertheless, based on the arguments we've already seen, this is representing the upper limit of what is possible in terms of efficiency. So at stage 4, the cold region can be removed, and at that point we continue with that 4-to-1 adiabatic compression, and at that point the cycle has returned to where it started and it can continue. Like I said, this is not possible in reality. If you tried to make this happen in reality, it would really take infinite time to achieve all the things that I've described as we went through. And you compare that to an actual practical engine that goes through a cycle really, really quickly. This does not do that.